Welcome to my contribution. It's about top-down engineering. My name is Markus Wache. I am working as a product lifecycle manager in the headquarters in Nuremberg. I'm responsible for some things on device side, as you can see, for the Bay controller 6MD, for the CFC, but also for the phasor measurement unit. And on the engineering side, I'm responsible for the top-down engineering functionality in DIGSI5. This is what I would like to present to you today. You may ask, what is it, top-down engineering? Don't worry, I will give you a short introduction about this top-down engineering 61850. Then I will present to you how DIGSI5 supports this top-down engineering. I will show you some use cases. Then we will go into DIGSI. Nothing is better in visualization in the tool itself, in DIGSI. And then the last point will be a short summary. So what is it about the top-down engineering? It's nothing we invented as Siemens or as DIGSI feature. It's something defined in the standard. You may know that the 61850 is much more than describing an interoperable communication protocol. It's also defining data models and also including the engineering. This is part 6 of the 61850. And the basic idea of this part 6 of the 61850 is that there is a language, a substation configuration language, SCL, which is able to describe a substation. So we are not talking only about configuring one protection relay, some settings maybe of a distance protection zone or such things. We are talking here about a substation including, of course, protection functionality. So this idea of the 61850-6 is that there is a system specification tool. You can see it here on the left side, and that you can create with that a substation description. The SSD file, which is described in this SCL language. This is XML based. We will see an example later. It has 4 main parts. The substation structure, this is the topology, for example, the bus bars, the voltage levels, the base, something very good, visible also for the humans. Then you can describe the devices, the IEDs. Of course, this part is very interesting for a tool like DIGSI, which has the task to configure these IEDs so that you can operate them. Then there is a part data types. This is quite theoretical and not well readable by humans. And there is a network part describing communication relations, like goose exchange of information, for example. So this is replacing other analog descriptions like Excel lists, drawings, etc. So this is a possibility to hand over your requirements to a manufacturer like Siemens. It is, of course, vendor independent. In this SSD file, it's not fixed that you need Siemens devices. It's a functional description, and it's, of course, because it's XML, it's machine readable. And DIGSI now makes use of this feature and helps you to copy or transport this information into the devices. Examples for such tools are Helix from Switzerland, H&S, it's a German manufacturer, or Calcitech. I show you this short list to show you that there is no Siemens tool here, because the intention is to be vendor independent. And so also these tools are vendor independent. Let's look a little deeper onto these 4 parts of such an SSD file. The substation structure contains the topology. You can visualize this. This is a small screenshot from a tool where I created a simple example with 3 bays. So you see here a double busbar system, 2 feeders, a coupler, some protection functionality. This is the basis where you start to define your substation, including protection functions already. The device, the data type section is next. This I can show only in XML. So here you can describe how you want to organize your functionality. The IED section describes what devices you want to have. So in this case, with the 2 feeders and the coupler, in this example, I selected 2 7SJ overcurrent protections for the cover of the feeders and 1 bay controller for the cover of the coupler. We will see this later in the practical example in more detail. And the network describes also very useful functionality which can be used by DIGSI. The subnets, the IP addresses of the devices, and the goose connections, for example. All these 4 parts can be there. They are not mandatory, so an SSD file can of course contain only parts of these content here. But this is the full content according to 61850-6. So how to make best use of it? Here you see again the figure from the first picture, but you see here a small addition on the bottom left. You can create with DIGSI so-called typicals in the ICD format. This is the IED configuration description. This can be used as typical in such a system configuration tool. It's also vendor independent, but it contains the description how we do it in Siemens. It's our suggestion. We don't start with a white piece of paper. Of course, if you use a device from the DIGSI library, you can export it also in this XML, in the SCL format, and use it then. And then you can create the substation in the substation configuration tool and then read in this into DIGSI, where you have the usual workflow in finishing the protection settings or device settings and exchanging, if necessary, the SCD with syscon if you want to change something in the gooses. And you then have the configured IED descriptions which you can load into the devices. DIGSI now supports some automatic actions here, which we will also see in the demo then live. We can create the device instances, we can rename devices, we can use, for example, the IP addresses from the SSD file. And to support this, we have included in DIGSI a new file type, the import in SSD format, which we will see in the example. The import specification is accessible under the 61850 entry in the project navigation view. So this is here since DIGSI 8.6, and we improved this feature in the last 3 versions, including the now fresh release 9.20. So this is a new editor. As I said, it's available since 8.60, so if you like, you can look in your DIGSI if it's there and then start exploring the functionality. If you click on this, an editor like this will show up. It's already filled here. The first step is always to select the SSD file here. I have done this, but on the right side it's still empty now. The idea here is to show on the one hand, on the right side, the input from the SSD or SCD. That doesn't matter, both is possible. It's the same file, just another extension. And on the right side, in this example, it's empty. On the right side, we see the content of the devices in the DIGSI project. Here we currently have a lot of red symbols, meaning the requirements are not fulfilled because no device has been selected. And the intention of this new editor is now to support the user in the best way to create the devices or instance devices, reuse them, and create the functionality from the requirements list from this specification file. Let's see first in theory how that can work. Here I have created a device which matches hopefully the requirements here, and I've mapped it here. So, and DIGSI in the first shot gives a partial green symbol, so that means a part of the logical nodes match, other parts may not match, and DIGSI supports now in detail to fill in the gaps here. So on the first step we could here create user-defined function groups. For example, GGIO or everything starting with S is functionality we usually create in a CFC that is user-defined. We distinguish here between the user-defined and the implemented functionality. Implemented functionality is, of course, the protection functionality, for example. Everything starting with P, the PTOC, the time overcurrent protection, for example. So here now you can click on these symbols here, the icons, the blue icons, which starts the creation of the selected functionality. Here a drop-down list shows what could match to a PTOC, or this functionality contains PTOC LNs, so it is selected in this drop-down list. So you see here it requires some knowledge because the device has such a huge variety of functionality, and this is why we recommend to work with typicals, so that DIGSI already works with the same basis like the SSD tool, this SCT, system configuration tool. However, if you did not do this, we also support and filter down here to the functionality which is available in the device. Then this is created here, and the nice thing is that this PTOC is then in the real device. It is created as functionality in the cProtect device, and also visible if you click in the device in the PNV, of course. You can then repeat it. It's also a sort of type here. It's a hierarchy, so if you click on the higher hierarchical blue button here on device side, everything what is offered here is clicked in the background, so you don't need to create these functionality LN by LN. You can click on the button of the higher hierarchy, and then the functionality what is selected here. This is a pre-selection by DIGSI, then GGIOs will be created, but it also works with selected functional LNs, for example the PTOC protection logical node. You will get a log, of course, where everything is logged what DIGSI did. You can check here, if you like, what has been done in the device, and then it is also available, as I said here, this is the PNV view of the device, and the functionality is created there. You see here the red icons have turned to green. Another very helpful feature which we supply independent from this SSD import also, but it's included here, is the creation of multiple device instances from typicals. So here in this example I can see here that in the SSD 3 bays are requested which are based on the same typical. So I need 3 cProtect devices in my DIGSI project. Then I can use this functionality, attach DEX files. That means somewhere I have prepared the fitting devices and exported them in the DIGSI format. This is our Siemens manufacturer format, which describes fully the device, including product code and the CFC and the display pages, what is not possible in this SCL format, of course. So then I get a dialog where I can attach via the browse button this DIGSI file. It is then added 3 times, so it's one click and added to all these 3 boxes here. And if I click then on import, these 3 devices will be created in my DIGSI project, and they will get renamed like in the SSD file. They will get the IP addresses from the SSD file, and they are ready for use. As you see here, they also fit then very well. They are then put into this box here on the right side of this new editor, and so they are related to this entries, to this required devices. And if the typical is well fit, then there should be all green on this detailed view in the editor. Let's come to the principal use cases. I have talked about empty projects, but also about the use of typicals here. So in principle, there are 2 use cases. The one is the import in an empty DIGSI project. So the task of DIGSI is then select the protection devices, map to this IED section of the SSD file, and adapt the functionality. DIGSI supports in this new editor in finding and configuring the cProtect device. If you have an empty project and no DIGSI files, you need, of course, a certain knowledge. You must select by the requested logical nodes protection functionality. If there is a PDIS, a PTOC, the type of device. No? You need a little knowledge of 61850 on the one hand side, which protection functionality is needed, and a basic knowledge of our cProtect library, which device to select, so that you don't always need a 7SL, the maximum device, what we have, or 7SX maybe. The second use case is that the SSD uses available typicals. Then the task of DIGSI is simpler. It's to reuse the typicals, which should be available in the DIGSI format, to create this substation instance. You can also start with an empty DIGSI project, but DIGSI automates then the creation of this substation instance. And we will look to this use case in our practical example following soon. Let's have a more detailed look here on our practical example. As I said, I start with an SSD file with 3 bays, which I have prepared. There are simple protection functions. 2 bays use time over current protection, and the coupler is just a bay control functionality. This I have put together in the Helix tool. It's quite simple and exported as an SSD file. For one of the 2 protection devices, I have used the library, the protection library from the Helix tool, and from the second, for the second device, for the second bay, I have used an ICD exported by DIGSI for an 7SJ85, which is the best fitting device here. This is my suggestion here. So that you can see the difference between using an ICD file from DIGSI on the one hand side and using the library content from the SCT tool, in this case manufactured by Helix. It may be different if you use a different tool on the one hand side, on the other side. The SSD file you can open with an XML editor. It is a little bit readable by humans if you don't open too much details here. You see here, you see the base and the topology. You see the IED section. There you can get also an idea that one is different. It's the manufacturer is Siemens is shown here. The other tools, the manufacturer seems to be the manufacturer of the tool, but of course cannot be the case, but what to enter there elsewhere. But if you open all these small plus signs here, you will end up in a file having nearly 8,000 lines, even in such a simple example. So this is a very good good task for a tool like DIGSI to automatically read in this. If you would have to check all these 8,000 lines when you configure the devices in DIGSI, that doesn't make sense. Okay, so we will start with this import specification functionality. We create these devices and let's do it in DIGSI to get a better feeling here. I have prepared the DIGSI. I need my reading glasses to work on my screen. What we will do here is to start with an empty project, but I have in the background prepared the DIGSI files, so I don't have to do all the work here on the screen. I will show you to create the devices according to the requirements from the SSD tool. So we will have the empty project. We will open our example SSD here. And there we can see there is a topology section having the voltage level, the 2 bus bars and the 3 bays appear here. We can click downwards and you see all these objects which you have already seen in the topological view of this double bus bar system. If you click down here, also the devices appear which are mapped to it, but of course the much better possibility to work on the devices is this IED section which follows after the topology section here. And you can see here that we have here already the description of the 7SJ. So the DO2 device is based on the ICD of Siemens, and the DO1 is based on the suggestion from the Helings how to build such a device. If I click here and compare, you see there is of course a huge difference here. We have already modeled our measuring system, and here it's only a very standardized view here. So we start with reusing my SSDs. For the DO1 and DO2, I would like to use the prepared 7SJ. And for the DO3, I use the prepared 6MD85. I click on import. We create now 3 devices and rename them as they are requested here. This will take about 2 minutes. So you can imagine that this is already a huge improvement because the normal substation doesn't contain only 3 devices. This of course works also with a higher number, and it's already a huge improvement for larger substations. If there would be gooses in the SCD, they would also be already copied to the devices and reused there. So we have now the 3rd device. It should be ready soon. And then the devices appear in the project where we started without any device. You see them now appearing here in the tree, and they have already the names according to the SSD file here. Let's have a look on the mapping suggestions here. So we see here something green, and we can also see that there is a difference. My resolution is not the best here, so I have to click here a little bit. You see here the match of the device DO2, which is based on the SCD, is much better than for device 1, where we have 7 matches, and here we have all matches. There are only some details missing here. So of course, if I work with the same ICD on the SCT tool side, we have a nearly full match. Just here, where I changed something, I can show you how to create some missing data objects. You see here, even on the functionality, we have the full match. Only one block stage is missing, where I can click here on creating the object, and then it is created. So we have then here the full match. This is the example how you can detailed work here. And yeah, I don't want to do this fully for everything. For the bay control here, DIGSI suggests something, so the circuit breaker is matched. The LD0 is the application node. This was not found, but we are currently continuously improving this algorithms here. So you see here you have to do a little detailed work to find the LPHD0, but it is suggested by DIGSI. You can create all of these, and maybe you get some warnings because the Helix tool here suggests all data objects which are described in the standard, and of course some of them are mandatory, and those who are optional, we do not completely 100% support them, and these are some gaps which are remaining here. But nevertheless, of course, the Siemens devices are standard conform. Okay, so this is what I want to present here, what I can present in the time slot. So we support here. One message is it's clever to use ICDs for the tool. Otherwise, you start on a blank page and you need to do the detailed device work later here. And the other thing is here you have a very powerful possibility to fill the gaps and to adapt the devices to the requirements of DIGSI. Let's return to the slide set and come to the summary. So this top-down engineering, according to 61850-6, offers digitalization of substation automation and protection engineering. It's faster and it's automatic instead of having manual data exchange. That, of course, avoids errors. Typical based approach is most effective, but I think you do that anyway. And a hint from manufacturer side, use a library of existing devices based on ICD files in the system configuration tools. Thank you for your attention.